multiplication examples, because I think it is all about what may seem to be a more difficult problem, and it might not be even clear that we can multiply these matrices. First thing we should think about. So let's say I wanted to multiply the matrix. I'll do it relatively small so we don't run out of space. 3, 1, 2, minus 2, 0, 5. And let's say I want to multiply that times the matrix minus 1, 0, 2, 3, 5, 5. I'm just making up these numbers. So the first thing you might be wondering is, well, can I even multiply these matrices? Because you know from the first video we did on matrices that you can't add these two matrices. You know, this term corresponds to this one corresponds to this one, but this term corresponds to nothing over here, so you couldn't add or subtract these matrices. So the question is, can I multiply these matrices? Well, what did we learn about multiplying matrices? We know that, for example, if this is going to result in some matrix. However, we don't know even what the dimensions are yet until we work through this example, although there's a quick way of figuring it out. So this first term here, the upper left term, where does it get its row information from, and where does it get its column information from? Well, it gets its row information from here. So it's essentially this row times which column? Times this column. Right? And we can actually take the dot product of this row vector and this column vector because they have the same length. This is a column vector, but it has a length of 3, right? It's a 3 by 1, but it has 3 elements in it. And this is a 1 by 3 row vector, but it also has 3 elements in it. So we actually can take the dot product, or we can multiply these two. And similarly, we can multiply this times this whole thing to get this term right here. And then we can multiply this thing times this thing to get this term, and then this thing times that term to get that term. So it actually turns out that you can. So what kind of a matrix is this? Let's call it that this is matrix. Let me switch an arbitrary color. So this is matrix A. And what are its dimensions? Its dimensions are, it has 2 rows, 1, 2, and 3 columns, 1, 2, 3. So it's a 2 by 3 matrix. It's a 2 by 3 matrix. And we're multiplying it times B. B. And what are B's dimensions? Well, it has 3 rows, 1, 2, 3. So it's a 3 by, and how many columns does it have? 1, 2. 2 matrix. So it turns out that we can multiply two matrices if you can kind of say that the number, if on the first matrix, the number of columns is equal to the number of rows in the second matrix. So here, 2 by 3 times 3 by 2, we can multiply them. For example, we could have multiplied, if this is matrix C, I don't know if I take so much time to keep bolding these things. And I don't care how many rows it has. It can have n rows, n times a columns. I can multiply it times matrix D as long as matrix D has a rows. As long as you can kind of say these two inner numbers are the same, right? This 3 is the same as 3. And why does that matter? Where's the logic? Because this row will have 3 elements because there are 3 columns. And each column vector here will have 3 elements because there are 3 rows. That's the intuition comes from. But if you have to do it real quick, you say 2 by 3, 3 by 2. This number is equal to that number. I can multiply. So let me clear up some space and let's do the multiplication. Let's do some multiplication. Let's do some multiplication. I'm debating where I should do it. I think I should do it down here maybe because I'll have more space. So let me do it down there. I don't have to erase anything else. So let me get some space ready. Okay. This will take up a lot of space. So to get this row 1, column 1 element, what do? I multiply this vector times this vector. I take the dot product, right? So it's 3 times negative 1. I'm just going to write it all out. 3 times minus 1 plus 1 times 0 plus 1 times 0 plus 2 times 2, which is, well, I'll just write it 2 times 2. There, we got the first term. So the second term here, what am I going to do? I'm going to multiply that vector times that row vector times this column vector. And I think you're getting the hang of this. And it's really the hardest part about this is just not, staying focused and not making a careless mistake. And not getting confused with rows and columns and all that. So it's a bit of a, just kind of sends blood to your brain, but it's not that hard, I think. So what do? We multiply this row vector times this column vector to get row 1, column 2, right? Because this row, row 1, column 2. 3 times 3. So it's 3 times 3 plus 1 times 5 plus 1 times 5 plus 2 times 5. Right? We're just kind of multiplying the corresponding terms, although, the third times not the third term, the second term times the second term, the first term times the first term, although, in this case, they're kind of going down, in this case, they're going left and right. And we add them all up. Okay, so now we're in second row, and we get our row information from the first vector, and let me do a red that I never use because I think it's kind of tacky. But this red right here, so I'm going to multiply this row vector times this column vector. So it's minus 2 times minus 1 times minus 1 plus 0 times 0, 0 times 0, plus 5 times 2, plus 5 times 2. We're almost done. Let me see, I don't like this color at all. And now we're going to multiply this row, because we're in this bottom row. We're in row 2, column 2. Row 2, column 2. So it's minus 2 times 3. Minus 2 times 3 plus 0 times 5 plus 0 times 5 plus 5 times 5 plus 5 times 5. And then if we simplify it, let's see, minus 3 plus 0 plus 4. So this is, if my math is correct, this simplifies to 1. 9 plus 5 is 14 plus 10 is 24. This is 1, 24. And then minus 2 times minus 1 is 2 plus 10. So this is 12. Right? That's 12. And then minus 2 times 3. That's 6. Minus 6 plus 10. This is 0. So minus 6 plus 10 is 4. So that's interesting. When I multiplied a 2 by 3 vector times a 3 by 2 vector, what did I get? I got a 2 by 2, matrix. A 2 by 3 matrix. 2 by 3 times 3 by 2 matrix. I got a 2 by 2 matrix. And where do you see a 2 by 2? Well, it's kind of like this got multiplied with this, and what we have left over is a 2 by 2 matrix. So in general, well, actually, before I go into the general, let me ask you a question. Could I have multiplied the matrices the other way? Could I have multiplied? So this right here, that is A times B. Or you can sometimes write just AB, and we'd bold it all up so we know it's matrices. So could we have multiplied B times A? Let me clear this down here, and let's try. Let's see if we can multiply B times A. And I think you can already suspect that since I'm asking the question, maybe you cannot. So let's see. Let me clear up some space. Let's try to do it the other way around. Let's try to multiply B times A. So B is minus 1, 0, 2, 3, 5, 5. And A is, I'm just switching the order, 3, 1, 2, minus 2, 0, 5. And I tend to put brackets around my matrices. Some people have these big parentheses. It's just all notation. There's nothing particular about notation. So let's see if you can multiply these. So we learned that you get the row information from the first matrix and the column information from the second one. So this term, in theory, should be that row times what? Times, well, actually, it turns out that you can multiply them. I didn't, because why? Because this is a 3 by 2, and this is a 2 by 3, right? So we're going to take that row times what? Times this column to get the first term, right? So what is it going to be? It's going to be minus 1. So I actually thought I was doing a counterexample, but actually because this 2 is the same as this, or when you switch the row, this is the same as this, it actually you can multiply them. So I wanted to do a counterexample, but hey, let's just work through this because it never hurts to see another example. And as you can see, I do this on the fly. So let's do this. And actually, just as ahead of time, how large will this matrix be? Well, this is interesting. It's actually going to be a 3 by 3 matrix. This is going to be a much bigger matrix. So let's work it all out. And maybe you want to pause it and try it yourself. So it's this row times this column. So minus 1 times 3. It's minus 3. So this is minus 3. And this 3 times minus 2 is minus 6. And then it's going to be this row times this column. Much bigger matrix. So let's work it all out. And maybe you want to pause it and try it yourself. So it's this row times this column. So minus 1 times 3. It's minus 3. So this is minus 3. And this 3 times minus 2 is minus 6. And then it's going to be this row times this column. So it's minus 1 times 1 plus 3 times 0. So that's just minus 1. Right? Because 3 times 0 is 0. And then, so that was that one. Then we have the middle one, and now we have the row 1, column 3. So row 1, column 3. So it's that row times this column. You can tell this is often better done by a computer. Minus 1 times 2 is minus 2 plus 15. 3 times 5. So minus 2 plus is 13. Let's keep going. So now we're going to take... I'm sweating. This is so computationally intensive. We're going to take this row times each of these columns. And actually, we're going to learn later that there's multiple ways of actually kind of thinking about how this multiplication happens, or even multiple ways to compute it. But this is the traditional way. So this row times each of these columns, right? So 0, 5. So 0 times 3 plus 5 times minus 2. That's minus 10. If 0 times 1 plus 5 times 0, that's easy. That's 0. 0 times 2 plus 5 times 5, that's 25. Almost there. Almost done. Now we're going to take this row and multiply it times each of these columns. So 2 times 3 plus, so that's 6 plus minus 10, so that's minus 4, right? 2 times 3 plus 5 times minus 2. Yeah, that's minus 4. 6 minus, right? Then you have 2 times 1 plus 5 times 0, that's 2. Then you have 2 times 2 plus 5 times 5. So 4 plus 25, 29. And of course, that first term, minus 3, minus 6. So this is minus 9. So there you have it. We multiplied a 3 by 2 matrix times a 2 by 3 matrix, and we got a 3 by 3 matrix. And where did that 3 by 3 came from? Because this 3 is the number of rows in the first matrix, and this 3 is the number of columns in the second matrix, which makes sense because we got our row information from the first matrix and our column information from the second matrix. Now, let me actually show you an example that you cannot multiply. So what if I wanted to multiply let me do a very simple example. What if I wanted to multiply the matrix 2, 1, and really all this is a row vector. And let's say that I wanted to multiply this times, I don't know, so this is a 2 by 1. So then let me say I wanted to multiply this times, so let me think of something. 1, 2, 3. 1, 2, 3, 4, 5, 6. Now, can I multiply this? Well, what do we, and this is what? This is a 3 by 2 matrix. Can I multiply these two matrices? Well, what do we have to do? We get our row information from here and our column information from here. Oh, sorry, this isn't 2 by 1. This is 1 row, 2 columns. This is a 1 by 2. Right? That's a 1 by 2 matrix. So can you multiply the 1 by 2 times a 3 by 2 matrix? So we get our row information from here. So we essentially have to multiply this times this column to get our first element, then this times this column to get our second element, and I don't know what happens from there. But can we multiply? Can just the way we've defined our multiplication, or the dot product, can we multiply? Let's see, we do 2 times 1 plus 1 times 2, but then we don't have anything to do with the 3. So the way that we've defined matrix multiplication, you cannot multiply these two matrices, and you didn't have to go through that exercise. You could have looked at the dimensions. 1 by 2, and this is a 3 by 2. This 2 is not equal to this 3. The number of columns in the first are not equal to the number of rows in the second, so you cannot multiply those two matrices. So that's something interesting to think about, and there are actually examples, and it's a good exercise for you to think about it, where you can multiply them, where you can multiply A times B, but you can't multiply B times A. So, and I want you to think about examples where that happens. But anyway, I'm pushing 15 minutes, and I will see you in the next.